All right, hello. So for project 1, we are going to assess the ability of the van der Waals, SRK, and Peng-Robinson cubic equation state to predict vapor-liquid coexistence. And so we're going to assess their ability by comparing to reference data available by NIST. And so all of you have been assigned a set of systems, and in all, together we will look at every single system for which data is provided by NIST. So what I'll walk you through in this screencast is I've created MATLAB code to automate the prediction part of this for you. And so what I'll walk you through is how to make predictions, how to download the data from NIST, and then how we can take all of the output from my code and copy and paste that into a Google Sheet. Okay? And so I want all the data that you generate to be stored in this team drive so that we all have access to each other's files. Okay, and so I'll show you how to do all of the calculation part, get all the data NIST or for NIST and all of our predictions in our Google Sheet, and then what I'll leave up to you is performing the analysis. So assessing how well the cubic equations of state performed compared to the reference data and generating the figures. I had this in the original version of the MATLAB code, but removed it so that essentially I force you to actually look at the data, play with it, and hopefully get those wheels churning in terms of assessing how well we did. Okay. All right. So I created a team drive for us. So it's the CPB 412.512 Spring 2019. So I'm going to open it up. And right now there's just one folder for project 1. Okay. So I'm going to open that up. Okay. So the M files that I have created are in this M files directory. We'll download those in a second. And then right now there's just this Google Sheet system assignment. If I click on it, it has all of everybody's who's in the class in alphabetical order, and then I just cycle through all the systems for which data is available on NIST and assign them one by one to everybody. Okay. In terms of this fourth system, some of you have been assigned a fourth system, some of you have not. So those of you who have not been assigned a fourth system here, we'll try and balance it out in later projects. But if you have a fourth system, personally I don't see it as being much in terms of extra. So I have code that'll do the analysis for you. So it's just a matter of running the code and then performing analysis for that additional system. Okay. If you have issues, let me know, and I am here to help. Okay. But the goal is I wanted to look at every single system for which there's NIST data, so that we could come together as a class and look at all of the data as a whole. Okay. All right. So I will start with water. All right. So water is the first system assigned to Louis. And so what I will do is I'm going to open up a new tab, and I'm going to do a Google search and just look for NIST thermophysical. Okay. If I press return, the first link that comes up is Thermophysical Properties of Fluid Systems, the NIST webbook. So I click on that, and I'm brought to our screen of interest. Okay. So so here's the URL up here, if you're not able to get it via Google search. Okay. And so I said I assigned all the systems for which data is available. All right. And so what I mean by that is if I click on this drop-down menu of, please select the species of interest, this lists all of the species for which data is available. Okay, starting with water, right at the top was the first one assigned. Okay, so one note is NIST has lots of data available for refrigerants. When I listed a refrigerant, I used the shorthand notation to say R11 in this case for the first one to correspond to this trichlorofluoromethane. Okay, so if you see R11, R12, R13, or so on and so forth, right? I just use that in place of the full chemical name. Okay, so you select your species of interest, and then next comes the units that we want to use for the properties that NIST is going to generate data for. Okay. So of interest to us is just temperature through energy. Okay, we don't do anything with velocity, viscosity, or surface tension, so I won't mention those at all. So temperature, we want things in units of Kelvin. Pressure, we'll use units of bar. Density, moles per meter cubed. And energy can be kilojoules per mole. So make sure you have Kelvin, bar, moles per meter cubed, and kilojoules kilojoules per mole checked. And if I scroll down to the next section 3, choose the desired type of data. So you want saturation properties. So we're looking at vapor-liquid coexistence. And then for VLE, our two options are temperature increments or pressure increments. Okay, so select temperature increments. So this will make it so that the NIST generated data agrees with our cubic equation to state predictions. So if you remember from your homework, right, the general idea is you fix a temperature and then you essentially guess a value of pressure until you find the pressure for which your equality of fugacity coefficient criteria is satisfied. Okay, and so choose temperature increment, so data is generated in increments of temperature, and when we'll do the same, temperature increment when it comes to calculating properties using our cubic equations of state. Okay, last is standard states. All right, we've talked about standard states in class. Here, it's not really all that important. Right? What we're going to take from NIST is temperature, pressure. We'll calculate compressibilities from the provided data, molar volumes, and enthalpy of vaporization. So the only place that reference state would be applicable is enthalpy, but since we want enthalpy of vaporization, it doesn't even matter. Okay, so press to continue. Okay, next I need to tell it the range, temperature range over which I want to make, I want data, and in terms of what temperature increments. Okay, so for T low and T high, okay, so the minimum value of temperature, which is provided in parentheses, essentially corresponds to the triple point. Right, triple point of water is 0.001 degrees C. Okay, and then T high is going to correspond to the critical point. Right, beyond that, there's no VLE. And so the T increment will be, you specify T low, it's going to go from T low to the T high you specify in that increment of temperature, right? So you want to make sure that your temperature increment is chosen such that you can go from T low to T high in a fixed number of steps, okay? Which leads us to how many steps or data points should I look at? Well, the more the merrier, okay? The only negative I would see is in terms of having more data is there's going to be more computer time related to generating the predictions. Okay, and so for water, this isn't a problem. Okay, so I want to look at data in increments of 10 degrees. So I'm going to go from 280. Right, I can't start at 270 because that would be below the triple point. And I'll go up to 640. I can't go beyond I can't go up to 650 because that'd be beyond my critical point. So I'll go to 280 to 640 in increments of 10 degrees. So I'll generate a large amount of data. Okay. When you have systems like nitrogen or non-condensable gases, the actual temperature range that you can look at is going to be much smaller. So try and choose or try and generate, if possible, a large number of data points. Right. So if I have at least 20 data points, that's great. Right? We just want, a meaningful number so that when we perform our analysis, we're generating statistics for, a reasonable amount of data. Okay. Again, right? The calculations are going to be automated, and in terms of analysis, right? You do in Google Sheets, you're just going to drag and drop an equation, so it really doesn't add much in terms of making the problem harder. So don't try and shortcut it. I press for data, and my data is instantly generated, right? And so NIST will provide this, cool little plotting feature. So right now, pressure is plotted against temperature, and yeah, it's great. But if I wanted to plot, instead of pressure versus temperature, density versus temperature, I could, right? And here I get, my phase envelope. Here's density versus temperature, liquid and vapor, right? Terminating up here at my critical point. Okay, cool. Okay, what I want to do is I want to download the data. Okay, so we can download the data as a tab delimited text file. That just tells us all the data points are separated by a tab. Okay. So I'm going to save it within project 1. Okay, you should create a directory with the name of the system you're looking at. So if you're looking at water, call it water. If you're looking at nitrogen, call it nitrogen. Okay, so eventually I'm going to want you to upload that entire directory to Google Drive. Okay. In my case, I created this directory example water because this is going to be an example directory for water, which I'll upload to Drive, which you can use as an example to follow. So I'm going to save this as water, and I'll call it NIST.dat. Okay. And I'll save it. Okay. If you want to know what it looks like, if I were to click on it, it should open up in your browser. It's just data separated by tabs. And actually, there's more data than I could fit within my browser, so it doesn't quite look as nice, but all the data is separated by tab, so all is good. Okay. Oh, if I were to open this up, so if I go to that folder where I've saved it, okay, water NIST.dat. So I'm on Linux, so it opens up with gedit by default, and it's the same thing. It's just every data point separated by a tab. Okay, so I'm going to close that. Okay, and that part is good. Okay, all right. The next thing I'm going to do is to this directory I created, in my case example water, you would create a directory for your system of interest. I'm going to go to this M files directory, and I'm going to download all of the M files that we have up here. Okay. So since I want to download all these files at once, it's going to zip it and then download, which is fine. Okay. But then I eventually want to unzip it and get all 4 of these files into my directory. So in my case, example water. Your case, it'll be named after your fluid of interest. Okay. So again, things might look a little differently on my computer using Linux, but it should all be the same. Okay. So here's where it downloaded. This is great. I'm going to extract it to, well, I need to search for where I've got everything stored. So I've got it in Dropbox, Project 1, this example water directory I created. Okay. So I'm going to extract there. If I go over there now I have the M files I just downloaded from Drive. Right, so there's an import sat VLE. That's just going to be reading in the NIST data and manipulating it to get it into a format compatible with our cubic equations of state results, and then files to perform calculations with van der Waals, SRK, and Peng-Robinson equation of state. Okay, cool. Okay, so these files, you won't need to touch them at all, but they need to be in that directory so that we can perform calculations for system of interest. Okay. All right. So next, I'm going to go over to MATLAB. Okay, and right now I have it. I've navigated my path to be in this example water folder. Okay, and I have the 4 M files that I downloaded from our team drive. I have my NIST data listed there, and then I have a script file on there, water VLE calc. Okay, so this will be provided in this example directory, which I'll upload at the end. Okay, and so you should also download this file to your directory of interest and rename it. So this is water VLE calc. So if you're doing calculations for nitrogen, rename it nitrogen VLE calc. Okay, it's a script. All that the script does is it's just going to automate performing the calculations. So there's only a couple of things that you need to update in the script that we'll walk you through right now. Okay, but you'll save a copy of this in your directory. You'll save a copy from my example directory and just make some minor updates to get it running. Okay. All right. So if I double click on it to open into MATLAB, okay, first thing I would update is I've just typed in the name of my system up here at the top so that I can remember what the heck this is. Okay. And then I have the script broken up into a couple blocks. Okay. The first is step 1. Right. I just need to tell MATLAB the name of a file from which I'm going to pull my NIST reference data. That's the data I just downloaded. And then the system name, which I'll use to create a bunch of output files, right? With that, is the leading name in the name. We'll look at what this exactly means. Okay, so in step 1, what you'll need to update is, first I'm assigning to this variable NIST sat VLE the name of the file that contains the NIST data I just downloaded. Okay, so I just downloaded it to a file called water NIST.dat. So this is type string, and so you should use single quotes to tell MATLAB what the name of your file is, right? In my case, water_nist.dat. Okay, and that file is assumed to be in the same directory as the script. The next thing you'll need to update is I'm assigning to variable system name what the name of my system is. This will be used just to create names of output files for which I'll save all of our predictions and our modified reference data. Okay, so you'll update those two variables. So just name of your file that you downloaded the NIST data to, and then system name. So this is water. If you're looking at nitrogen, you call it nitrogen. Okay. Step 2, in order to make predictions with my cubic equations of state, I need my critical temperature, pressure, and eccentric factor. Okay. So these are available in the back of your book, but what I'd like you to do is if I go back, and of course, looks like I already closed NIST. Okay. But let me bring back up NIST Thermophysical. Okay. And I'm just going to click through this real quick. So my apologies. Okay, so if I bring back up the data I just generated, underneath the table they have what's called auxiliary data. Okay, first is related to reference dates. Again, they're not important for our calculations, but then that's followed by these additional fluid properties. Right? It contains your critical temperature, pressure, and eccentric factor. Okay. When you perform your calculations, I would like you to use this value of Tc, Pc, and omega. Okay. And so here it gives you Tc in Kelvin, critical pressure in bar, and eccentric factor, which is dimensionless. And we want critical temperature in Kelvin and critical pressure in bars, right? But I'm trying to say is use these values. They should be consistent with the values in the back of your book. But take these just so if there's any discrepancies, we're consistent with NIST. Okay. So I'm going to take these values, okay, and that's what I'm going to type in here is my critical temperature, critical pressure, and eccentric factor. Okay. So you would update this for your system of interest. Okay. And that's all that you would need to do in terms of updating this script. Okay. So you don't need to touch anything below this. Okay. What I'll do is I'll just kind of peek at the rest of it so I can give you an idea of what it's doing. Okay. So I need to update step 1 and step 2. And then step 3, all it's going to do is this import sat VLE function. Again, remember, you don't have to touch any of these functions that you downloaded. Okay, it's just going to read in the NIST data, and it's going to take. Remember, NIST provides you a lot of data. We're just going to distill it down to the properties, common properties that we'll calculate with our cubic equations of state, namely temperature, pressure, compressibility, molar volume, and enthalpy of vaporization. It'll make sure everything's in the same units we'll get from our cubic equations of state. When it comes to compressibility, well, NIST doesn't exactly give it to you, but we calculate it from its definition of Z is PV over RT. And we calculate enthalpy of vaporization is enthalpy of my vapor minus enthalpy of my liquid. So it just takes the NIST data and it'll get it set up to facilitate comparing to our cubic equation of state reference data. And once it does that, it's going to write it to a text file. In this case, it would be water_nist_out.dat. And it's going to save it as CSV, comma separated vector. Okay, so we'll take a look at what that means. But all that means is we'll be able to copy and paste it directly into Google Sheet, and it'll be able to readily split it into columns. Okay, so it's a Excel-friendly format. I'd used XLS Write, but with MATLAB, XLS Write isn't compatible with Mac or Linux, only works on PCs. All right, so CSV is a good alternative. Okay, so it's going to read in the NIST data and then write out to data your NIST data in a format compatible with our cubic equation of state predictions. And then I'll perform predictions with van der Waals, SRK, and Peng-Robinson, writing the outputs to van der Waals predictions, SRK predictions, and Peng-Robinson predictions output files. Okay, and in terms of the calculations, for this exact case, to do all of this on my computer, it takes about 20 minutes. Okay, but it's not really computationally intensive, and so I was able to run in the background and go off and do other things. So hopefully it doesn't completely consume your computer. But for each system, plan on 20 to 30 minutes. Okay, but in that 20 to 30 minutes, it'll do all of the calculations for you. All that's left for you then is just the analysis in Google Sheets and generating some plots. Okay. All right. And so if you're not MATLAB savvy, you could just click the Run button up here since there's no inputs. Or for me, in my command window, I'm going to type water VLE calc. Okay, and we'll let it run for a little bit, and then I'll pause it. Right? And so see, it generated the NIST output. When it comes to van der Waals, SRK, Peng-Robinson, the calculations are a little sluggish, and they're mostly sluggish. I have it set up so we start at high temperatures and we work our way down to low. Okay, so the calculations at the high temperatures near my critical point are actually rather slow. And so the problem is if you think back to your homework, the idea is if I specify temperature, I then need to find the pressure for which the fugacity coefficient of my liquid and vapor are equal to each other. Okay, and so there was some systematic way we could go about that when solving interactively, but it's a little cumbersome and isn't really amenable to automating the calculations. And so what I use in MATLAB is F0. Okay, so I use a bracketing technique to solve for one. The difference in fugacity coefficient between the two phases is 0. And the issue with F0 and virtually all of MATLAB's optimizers is they can only handle real numbers. And so the slow part is I need to identify a range of pressures over which I'll get 2 real roots. Otherwise, these built-in techniques are going to fail. And so the slow part is just finding this range, right? And I don't do anything fancy. I literally just start from high pressure and start marching down my pressure range until I find this crossover from just 1 reel to having 2 reels. Okay. So at high temperatures, it's a little slow. So the first few data points is a little sluggish. After that, it's virtually instant. And what happens is once you get away from your critical point, you can just set your lower bound to be essentially 0, or 1 times 10 to the negative 15 is what I use. And that works as a lower bound. And so there's no need to do a complete search for that range. Okay. But anyways, right now it's working through van der Waals. I have it set up so that after each calculation, it updates, right? So this is going to be the massive matrix that's ultimately filled in. So here, first column is my temperatures. So I have it set up so that every time it completes a calculation, it prints the updated matrix. And so you could use that to essentially track your progress. Okay. First few data points are going to be slow, but then after the first handful, it's going to be rapid. Okay. So I'll pause this, okay? And again, I expect this to take about 20 minutes on my computer, but I can go off and do other things on my computer. It won't consume everything. But then once it's done, we'll come back and we'll look at the output and what to do with the output. Okay, so I'm just going to pause it and we'll come back.